This is the frequency response Bode plot of the band stop filter. So we can see from the amplitude and phase curves, the first part of the Bode plot is amplitude, second part of the plot is phase curve. So you can see here, so here also the same, you have two cutoff frequencies. This is the lowest cutoff frequency, this is the highest cutoff frequency or upper cutoff frequency. In the center we have FC, that is the center frequency or resonant frequency. So here FL, FH and FC are the same as those used to describe the behavior of the band pass filter. So here you can see here this FL, FC, FH, you can, because this minus 3 dB level, if you make one line, then you can see this one will cut at this point and this one will cut at this point. And if you measure the frequency level, they are in the same level. And this is because the band stop filter is an inverted form of the band pass filter. So we can call this opposite or inverted version of this band pass filter. The definitions for bandwidth, pass band, stop band, and center frequency all are same as the band pass filter. So here also we have the pass band, we have the stop band, and we have pass band. Pass band means these frequencies are we are getting at the output. Pass band here also we are getting at the output, and this region, this range or the mid range of frequency, we are not getting at the output. So all other definitions are same as the band pass filter, because here we have the lower cutoff frequency, upper cutoff frequency, center frequency, pass band, and stop band, and we have the bandwidth. Here this bandwidth is indicating whatever the frequency we do not want. But in the band pass, it's the opposite. The bandwidth is indicating whatever the frequency we want. Okay. So we can use the same formulas for all the calculations. The 1 by 2 pi RC and FR is equal to square root of lower frequency, lower cutoff frequency multiplied by higher cutoff frequency. So the same FL multiplied by FH. And the cutoff frequencies are FL is equal to 1 divided by 2 pi RC, the same. Okay, so now you can also see the phase shift. How is the phase shift? So here in this first part, we have the phase shift is lagging 90 degree. And the second part of the filter above this resonant frequency, the phase shift is leading 90 degree. This is also opposite from this band pass. Here is lagging 90 degree. Here it's leading 90 degree. Okay. So this is the same band stop response. And of course, this is really up to you. Here you can see the bandwidth is quite wide. We are rejecting. Instead, if you want to really very narrow band, you want to reject. For example, you have the DC motor control. For example, let's say DC motor plus minus, and you have the control circuit, and you are applying the input here. So let's say here control circuit plus converter circuit. Here I am applying the 230 volt, 60 hertz as the input. So now this DC motor is running in 1000 RPM, rotation per minute. Okay, so 1000 RPM. So now I want to reduce the speed of this motor to half of the speed. So now it's 1000. So I want to make it to 500 RPM. I want to reduce the speed of this motor. But I am applying here this converter circuit is, of course, I have some kind of a rectifier that will convert this AC into DC. And then I will also use some kind of pulse width modulation and reduce the pulse width and controlling the amplitude. And when I send this controlled amplitude here, after I convert into DC, then definitely the EMF reduced in this machine will be reduced also. EMF, there is the electromagnetic field, because all the motors and generators are running based on this EMF around its rotor and stator. So when we reduce this EMF, the speed will be reduced. So why we are talking about this one as an example? Okay, so I am giving this signal, right? This voltage, a reduced EMF, I am supplying to this DC motor. But what is happening here? I get this 60 hertz spikes, 60 hertz spikes in this input voltage to this DC motor. So spikes means that is like this. So the input signal is maybe it's going like this DC. In this input voltage which I am applying to this DC motor, suddenly I have some kind of spikes. Spike means that is a large amplitude with a short duration. So large amplitude with a short duration, it seems like a trigger, but it's unwanted spikes. So these spikes can create some kind of unwanted operation in this DC motor. So I do not want to have these spikes in the applied input voltage to this DC. So I need to filter these spikes out. So I need to smoothen this DC voltage. So I want only the smooth DC voltage I want to apply here. Maybe this motor need plus 12 volt DC. So I want to apply just smooth DC. This is the plus 12 volt. I do not want to have any spikes. So these spikes are corresponding to maybe 60 hertz. So what I can do here, I need to use the filter. So I can use this kind of band reject filter or band stop filter. This band stop filter I will design, it will only reject 60 hertz. So it will reject or it will block these 60 hertz spikes, and I will get at the output very smooth plus 12 volt here. And then I will add the filter here, and then I will get a smooth DC, and then I apply this, and then I can control this DC motor speed accurately or very clearly. So this is one of the functions. So why I am talking about the 60 hertz example here, we are talking, so we talk about the notch filter. Notch filter is nothing but band stop filter. So if you really reject very, very narrow band of frequencies, then this band stop filter is called as a notch filter. So in this kind of, for example, in this kind of control circuit, I use a notch filter to reject these 60 hertz spikes. So or we can also call this as a noise. So the filter will block these things, and then you will get the pure DC, and it will run this DC motor. So this is how we can design this band stop filter and use in the practical applications. We really need filters in most of the electronic circuits.